Hello again, everybody. Hey, I want to apologize. I called you my furry friends last time, and most of you really aren't furry. Um, and those of you that are, you know already, and you kind of know when you need a shave. So, I didn't mean to put everybody in that category. I apologize. All right. So today we are going to do vector components, or breaking apart our vectors. Now this is a little weird and I apologize. I got to give you all this math before I kind of tell you why, but we're going to get there in the next video lecture. So just hang on for one and then it will all become clear very soon. So hey, look at me. I'm fancy. I made graph paper. I didn't make it. I just stole it and put it on my page there. So, all right, let's start with any vector. But let's just add some axes, an x and a y axis. Notice they're not labeled, or they're not scaled with numbers and everything. They're labeled x and y is all. And I just drew a vector A on there. Let's pretend that vector A is the displacement vector for me when I walked to the store. It doesn't matter. So my house is at the origin, and the store is going to be out here where I ended up. So I started at the origin and I walked to the store. Now remember, this doesn't tell us anything about the path. My path could be like this, right? My displacement is only from the start to the finish. And if I'm fancy, let's see if I can get rid of that. Oh, yeah, look at that. Now, here's what we're going to talk about. I could have gotten to the store by walking on the streets, and the streets happen to be lined up with the x and y axes. So, for example, I might have first walked like this, straight down to there. And then I might have stopped, turned, and gone straight to there. And I still would have gotten to the store. I would still have the same displacement. I would have had to walk a little further than walking in a straight line, but I would have gotten there. Check it out. Pretty easy. What if I had gone up or north first? Usually up on a map is north. All right, I could still get there. That vector wasn't so good. Neither is this one. Sorry about that. I could get there by walking these directions as well. Okay, that's pretty straightforward. Now, can you see that the two green vectors are equivalent? They are the same. I can move them around. Same with the two red ones. Same length, same direction, so everything's fine. Now, here's kind of an odd way of looking at this, but hang on with me for a minute and see if you can get it. Let's pretend I took a flashlight and I put it way, way, way up at the top. I'm going to make my flashlight red. I put it at the top of my paper. Maybe it was as big as the sun. See a little curve I'm writing up there? And it's shining down, and all the light's coming straight down. If my vector A could make a shadow down onto the x-axis, the shadow would be exactly as long as that red vector, right? So one way of looking at this is that that red vector is the part of my vector A that's in the same direction as the x-axis. It's how much of A points along the x-axis. Does that make a little bit of sense? So I'm going to call my red vector A with a little x, because it's how much of A is in the direction of the x-axis, A sub x. And since the one on the top is equivalent, I'm going to label that the same. Both of those are A sub x vectors. Okay? Now, let's get rid of my sunlight from up there. I'm going to put the sun over on the right side of my paper. There it is. We're going to do the same thing in the y direction. The green vector is how much of my vector A is in the direction of the y-axis. So it's going to be A sub y. It's a little tough, but it's a really important concept. All right? Can you see that? A couple other things. AY and AX are perpendicular to each other. So we have a right triangle. Can you see that? If we take an AX and an AY and our A, we have a triangle with a right angle on it. So our right angle in our triangle is there, or it could be up here as well. Can you see they're the same triangle, actually. Alrighty, so that's the first idea I want to try to get across. Now, the next one is where things get not quite as much fun. I want to figure out how long AX and AY are. How many blocks did I have to walk in one direction, and how many blocks did I have to walk in the other direction? Now, in a lot of our problems, they're going to give us the angle between our vector and one of the axes. Usually it's the x-axis, but not always. But most of the time it is. So can you see I labeled the angle theta? Do you remember that from math class? We use that goofy symbol of a 0 with a line through it, or an O with a line through it, to be theta. It's an old Greek letter. That's theta. I don't know who got to choose that, but that's what they chose. Probably some really old guy. Alrighty, so here's what I'm going to do to find out how long those components are, the AX and the AY. Those are what we're going to call the components of A. One component is in the X direction, the other component is in the Y direction. I'm going to steal the triangle. I copied all those lines down and just made a triangle out of them. Okay? Now I'm going to do something here that's a little different than your math classes. Okay? A vector A has a magnitude or a size, that's how long it is, and a direction. All right? When we draw it, we give it its direction. Now, a lot of times, when you want to write the magnitude of a vector, okay, a vector's magnitude of, let's say, vector A, we write it like this. Okay, we put two lines across on either side of it. That's going to be really cumbersome. So for us, we are going to write the magnitude of A just as A sometimes. Okay, now that's technically maybe a little wrong, but that's what we're going to do. So if we just write our magnitudes here and just talk about our triangle, the length of this is A. The length of the green side is A in the Y direction. The length of the red side is A in the X direction. Now notice, I took the axes off as well. So all we're talking about is a triangle here. Okay? So now comes the part you're going to hate. I'm sorry about that. Does anybody remember SOHCAHTOA? Ah, I can hear the screams from here. The sine of theta, by definition, is the opposite side divided by the hypotenuse of the angle. Okay? Forgot to put our little right angle on here. So, the opposite side is, whoops, let me bring my triangle back so you can see it. The opposite side is a sub y, and the hypotenuse is a. Now here's what I want to do. Let's get a sub y by itself so we can solve for a sub y. So all we do is we multiply both sides by a, and there we go. So if we happen to be given the magnitude of a, the length of it, and the angle, we can find the length of the a sub y, the length in the y direction. Exactly the same game in the x direction. I want you to finish this one and solve for a sub x. So go ahead and pause me, and when you're ready, start me up. Alrighty, there's the answer. Now, do not memorize these. That was just a little practice to get into things. Okay, here's what I want you to remember. The sign goes with the opposite side. Okay, and the cosine goes with the adjacent side. That's not spelled right. The adjacent side. You spell it right. ADJ, is that right? I don't think that's right either. Somebody will have to correct me tomorrow. Adjacent side. Alrighty? That's the big idea I want you to remember. Okay? Now the good news is this. It's about all the trig we have to do. So, yeah, we have to do just one more little thing with tangent, but I'm going to see if you can figure that out by yourself. Alrighty, here's your problem. And I didn't cover this problem in the lecture. I want to see if you can bring some trig back into your brain. If not, don't stress. Just go ahead and ask me in class. Hope you enjoyed this. Have an awesome day. Bye-bye.